In this section, we're looking at polynomial and rational inequalities. These are some topics that students typically have some difficulty with, so make sure you get the concepts of this section. So most notably, our objective's pretty straightforward here. Polynomial and rational inequalities, we will solve both polynomial and rational inequalities. And then after we get comfortable with the basics, we'll look at some word problem applications that involve polynomial and rational inequalities in the solution. So first up, when we talk about a polynomial inequality, it's just where we have f of x that's a polynomial function, and instead of equaling some constant, it's going to either be less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0. So some polynomial in an inequality statement, and we always want to get 0 on the other side. That's much more beneficial than any other number. So you'll see in my procedure for solving polynomial inequalities, what I just said, it's the first step. So no matter what the inequality looks like to begin with, you want to get your polynomial either less than 0 or greater than 0, or could be less than or equal to 0 or greater than or equal to 0. So in other words, get a 0 on one side of the inequality statement. Now, after you do that, you're actually going to go in and solve the inequality the same way you would solve an equation. So all the techniques that we have and how we solve out polynomial functions, whether it's factoring, whether it's quadratic formula, whether it's looking at a graph to find its x-intercept and using synthetic division to further break it down, any of those techniques are on the board as far as how we solve the corresponding equation. But the solution to those equations are called boundary points. They may or may not be part of the solution, but I guarantee you they will be points that separate solution intervals from non-solution intervals. That's why the book calls them boundary points. They're on the boundary of a solution region and a non-solution region. So we'll locate these boundary points on a number line, and thereby dividing the number line into intervals. And then we'll choose one representative number within each interval. So if I have boundary points of -3 and 5, a good point to represent the values in between those two might be a value of x equals 1. It's in between -3 and 5. Then we're going to plug those into the original polynomial inequality. And if it gives us a true statement, then that region is a solution. If it gives us a false statement, then that region is not a solution. Then we'll write our solution set, selecting the interval or intervals that satisfy the given inequality. So unlike with an equation where you're always just going to have like x equals 2, x equals -3, you're going to have an infinite set of values that are your solutions. And it's going to be a continuous set from some x value to another. It could be from -infinity to 5, union 13 to infinity if it's two sets. We'll have to determine that within each individual problem. Now, that's what this next thing is saying. If your inequality is strictly less than or greater than, then you're not going to have to worry about any brackets in your solution, so you don't include your boundary points. However, if you're going to have a less than or equal or a greater than or equal, those boundary points where the equation is equal to 0 actually need to be included in your solution. So you'll have to put a bracket around them in the interval notation. Okay, let's see an example. So this one I just have a strictly greater than, so I know I will not have any brackets in my final answer format. But I'm asked to solve the polynomial inequality x squared minus 2 is strictly greater than 20. Okay, first step, get a 0 on one side. So I subtract out 20. When I do that, I'll get x squared minus 2 minus 20. This was a typo up here, guys. I apologize. That was supposed to be x squared minus x is greater than 20. And this should be x squared minus x minus 20 is greater than 0. So imagine that 2 there is an x. And then you'll see that's why I put this down here. My inequality would be x squared minus x minus 20 is strictly greater than 0. Well, instead of worrying about the inequality, I worry about the equation where it's set equal to 0. So then I can say, well, once I can do that, then I can factor the left-hand side, as long as I remember that 2 is an x. X squared minus x minus 20 would factor to be x minus 5, x plus 4. And then I can say, okay, x minus 5, x plus 4, that's going to give me solutions of x equals 5 and x equals negative 4. Now, I went ahead and plugged in the 5 and negative 4 into a number line. Here's x equals 5, x equals negative 4. This shows you your intervals that you need to test. We need to test, so our possible solution intervals are any number from negative infinity to negative 4, or it could be any number from negative 4 to 5, or it could be some number between 5 and infinity. There's no way it's all three of those. Could be one, it could be two of them. We will check and see. So in order to check and see, I need to choose a test value within each interval. So the first interval I'm choosing is, well, let's test interval from negative infinity to negative 4. What do? I choose a number that's inside of that interval. You'll see my test value here is a negative 5. What do you do with that negative 5? You plug a negative 5 into the left-hand side of your inequality, and you can say, well, that's going to give me negative 5 squared minus x becomes minus a negative 5, and then minus 20. It's going to give me 25, and then I'll have plus 5, which gives me 30. 30 minus 20 is a 10. Well, I know 10 is a positive number. What does that tell me? It tells me that f of x is greater than 0 for any value that's within this region. Now, does that mean that that region is a solution? Let's go back to our original problem real quick. And again, remember, it's supposed to be x squared minus x minus 20 is greater than 0. Well, any positive number is greater than 0, so I know absolutely this is telling me that this interval for between negative infinity and negative 4 is a solution because I needed it to be greater than 0. It is greater than 0. Okay, what about the set of numbers between negative 4 and 5? Anytime 0 is inside of an interval, I always choose it as the test value. So when you evaluate your function at 0 here, you can see, well, it's just going to be 0 squared minus 0 minus, that's going to give me a negative 20. Is that a solution? Well, of course not. Why not? Well, a negative 20 is going to be less than 0. Is that what we wanted? No, we wanted it to be greater than 0. So I can say, well, then the region between negative 4 and 5, that gives me a negative value that'd be less than, can't be a solution region. So right now I can say, well, the numbers between negative infinity and negative 4 are a solution because a test point in that region yielded a true statement. The numbers between negative 4 and 5 are not a solution because a test value in that region gave me a false statement. Now, if I plug in a value between 5 and infinity to test that, I chose a 6. So I plug a 6 into my function. I have 6 squared, which is 36, minus 6, which takes me back to 30, minus 20. That's going to give me a positive 10. Well, again, any positive number is going to be greater than 0. That's what we needed for this problem. We wanted the inequality to be greater than 0. So I can say, okay, then my solution set is from negative infinity to negative 4, union 5 to infinity, because both of those regions gave me a true statement to my inequality. The region between negative 4 and 5 gave me a false statement, so it's not a solution. So that's just what I'm saying here. Based upon this step, we see that f of x is greater than 0 for the values between negative infinity and negative 4 and 5 and infinity. Therefore, the solution set to that given inequality, x squared minus x was greater than 20, is going to result to being the solution x is equal to negative infinity to negative 4, union 5 to infinity. Now, if you graph that on a number line, you can either use circles and dots or parentheses and brackets. In this case, just as in the interval notation, there's parentheses everywhere. You would have to put parentheses on your boundary points of -4 and 5, because those boundary points are when it's equal to 0, or in this case, equal to 20. And we don't want that. We want it to be strictly greater than, so we can say those can't be included. So you either put the parenthesis or the open circle there if you prefer the other notation. I actually like the open circle on the number line myself. Okay, up next, talking about rational inequalities. Rational inequalities, it's pretty much the same thing as a polynomial inequality, except of course on the other side of the function, f of x is going to be a rational function, and that presents problems in and of itself because you're going to have polynomials in the denominator, and you can say, well, anytime that polynomial in the denominator is 0, your function's not going to exist. So our boundary points that are going to be where our function changes from a solution region to a non-solution region, we're just going to say, well, our boundary points occur at the x-intercepts, which is where the numerator is equal to 0, or the vertical asymptotes, which is where the denominator is equal to 0. But it's the same solution techniques that we had before. And the very first step that we had before, you might remember, you have to get a 0 on one side. So I do that. In this problem, and this is a pretty tough problem, 2x over x plus 1 is greater than or equal to 1. I don't want to deal with that first step, trying to set it greater than or equal to 1. Absolute first thing I must do is get rid of the 1. So much easier to do. So I get rid of the 1 by subtracting 1 on each side, and that achieves the first step of any inequality problem, get a 0 on one side. Now, all I need to do is determine when the left-hand side is positive and when is it negative. When it's positive, it'll be a solution region. When it's negative, it will not be a solution region. In order to determine what's on the left-hand side, I need to get a common denominator. I know 1 is the same thing as x plus 1 over x plus 1. So you'll see I have 2x over x plus 1 minus x plus 1 over x plus 1. Now, I keep the common denominator of x plus 1. I subtract in my numerator. 2x minus x is going to end up with an x in that numerator. And then please remember, you're subtracting a positive 1. Well, then that's minus 1. Your numerator changes from 2x to x minus 1. Now we have the rational function x minus 1 over x plus 1 is greater than or equal to 0. Let me make sure you understand the solutions to this rational inequality are the same as the solutions to the original. It's the exact same inequality, but it's so much easier to work with. That's what I'm saying here. This inequality set greater than or equal to 0, it's the same thing as the original set greater than or equal to 1. Now that I have it in the form where the inequality has a 0 on one side, I can say, well, all right, the boundary points. The boundary points are going to be when this function is 0, that's going to be when the numerator is 0, or when this function is undefined, that's going to be when the denominator is 0. So you'll see that's what I've done on this next step, set the numerator and denominator of the f of x equal to 0. So f of x is equal to 0 when the numerator is 0. That's going to be a boundary point. And f of x is undefined when the denominator is equal to 0. That's going to be a boundary point. So both of these are boundary points. Now, let's go ahead and talk about the difference in these two boundary points. Are they both going to be boundaries between a solution region and a non-solution? You bet they are. Absolutely. So in that sense, they're both boundary points. But one is a boundary point that could be included in your solution, and one is a boundary point that could never be included in your solution. And you need to understand that. So in this problem, I need to allow values in which this function is equal to 0 be included, because it says this inequality can equal 0. So I already know when x is 1, that function is 0. That is going to have a bracket around it whenever I write my final solutions. What about x equals -1? No, you're always going to have a parenthesis around that. Why? please make sure you understand why. It's because if you try to plug an x equals -1 back into your function doesn't exist there. So it could never be part of your solution set. It will still be a value where your interval notation changes from a solution to a non-solution or vice versa, but it can't be part of the solution, unlike 1, which is part of the solution. Okay, so my two boundary points were -1 and 1. I go ahead and I think of those on a number line. That allows me to think of, well, then my solution regions are going to be values between -infinity and -1. Then I need to test values between -1 and 1. Then I need to test values between 1 and infinity. I start doing that. I look at that first region between -infinity and -1. Please notice I chose a -2 to represent that region. What do you do with a -2? You plug it into your equation right here. So you say, well, we need this to be greater than or equal to 0. When you plug a -2 in, you're going to get -2 minus 1 over -2 plus 1. That's what I've done down here. When I simplified that, I got -3 over -1, which is a +3. So now I get a positive number. What do we know about every positive number in existence? Well, they're all greater than 0. Instantly, I know that this solution is part of my answer. -infinity to -1 will be a part of the answer, and it's not going to have a parenthesis around the -1 since that's an undefined value on the original point, on the original graph. Now, I look at my next region between -1 and 1. I choose a 0 to represent it. It's certainly within those values, so it's a good representative value. When I plug the 0 in, it's really easy to evaluate. I just get a -1 over 1. So f of x is -1 when x is 0. So that means f of x is always negative for any x value in between -1 and 1. What does that tell you? Well, that tells you that this region is not a solution. We don't want f of x to be less than 0. We want f of x to be greater than or equal to 0. So I can say, well, then the solution region between -1 and 1, not part of my answer. I move on to the last solution region, or the last possible solution region, the numbers between 1 and infinity. You'll see I've used a 2 to represent that region. Nothing special about a 2 other than it is certainly within that region. You'll notice that when I plug a 2 into the equation, I get a 2 minus 1 for a 1 in the numerator over a 2 plus 1, which is 3 in the denominator. So I get the 1/3. Well, I really don't care what number I get. I just care about the sign of it. I know that 1/3, as well as any positive value, is going to be greater than 0. So the only thing I care about is that it was positive. All positive numbers are greater than 0. That is what this inequality wanted. It wanted greater than or equal to 0. So I know the numbers between 1 and infinity are a part of the solution. So now let me go back and say, well, I know that the numbers between -infinity and -1 were part of the solution because it was greater than there. And now I know the numbers between 1 and infinity are part of the solution. And I also need to keep in mind, keep in mind, in your test intervals, we always put parentheses in the test intervals for the test, because I don't want to use a test value of 1. That would be bad. This is just showing that 1 cannot be a test value. I chose a 2 as a test value. But now, can 1 be part of the solution to this problem? Absolutely. It can and should be. So whenever you're doing your solution set, and I apologize for the bad typeface here, the solution set for this inequality should be the numbers between -infinity and -1 union bracket the numbers between 1 and infinity. And that bracket there needs to make sense to you, because when x is equal to 1, your function is equal to 0. That's okay. -1 is not included because at the boundary point -1, your function does not exist. That's why there's parentheses around -1, brackets around +1. I certainly prefer the interval notation. If you used the set builder notation, it would be x such that x is less than -1, or x is greater than or equal to +1. On a number line, you could put a bracket around 1 and shade everything to the right, and a parenthesis around -1 and shade everything to the left. It's everything except the values in between and -1 itself. You could also put a dot and a circle there if you prefer that type of number line notation. Now, let's look at a polynomial application where we have a polynomial inequality application. It says, an object that is falling or vertically projected into the air has a height above the ground, and I'm just giving you a vertical position function here. S of t is equal to -16t squared plus v sub 0 times t plus the original position s sub 0. So, and what I just said, v sub 0 is the original velocity or initial velocity in feet per second, t is in time, and the object is in motion in seconds. And s sub 0 is nothing more than the original position, or in this case, since it's vertical position, it's just the original height. Now, looking at that function, let's think about how the following problem is going to come into play. It says an object is propelled straight up from the ground level with an initial velocity of 80 feet per second. Its height at times t is modeled by the height at times t, s of t, is equal to -16t squared plus 80t, where the height, s of t, is measured in feet and the time, t, is measured in seconds. So this is going to be in feet over seconds. In which time interval would the object be more than 64 feet above the ground? So you say, well, okay, we're just trying to find when the height or when the y value of this equation is going to be above 64. So pretty simplistic, I just set the position function of this equation and say that position needs to be more than. Well, more than means strictly greater than. So I'd say strictly greater than 64 down here. I'm just taking my equation, putting it in an inequality, saying it must be greater than 64. Now, remember, whenever we deal with an inequality, it's so much better to deal with an inequality where 0 is on a side. So I said, well, an equivalent inequality to that is if I would subtract 64 on both sides and just get -16t squared plus 80t minus 64 is strictly greater than 0. Now, what I'm going to do is I'm going to find the x-intercepts or the values of this function where it's equal to 0. So I do that. So if I'm trying to solve out -16t squared plus 80t minus 64, if I'm trying to find out when it's greater than or equal to 0 to solve the original inequality, then I forget for just an instant that it's an inequality and I solve the corresponding equation when it's equal to 0. Now in this case, and in several of the applications in the book, it's not bad at all to factor because we can use the greatest common factor. I can factor out the leading coefficient of -16. 16 goes into 85 times, into 64 4 times. I'm factoring out a negative, so this is going to be a -5 and this will be a +4. So I get -16 times t squared minus 5t plus 4. Now I'm looking for factors of 4 that sum to get to -5. And I say, well, that's -4 and -1. So I get factors -16 times t minus 1 times t minus 4 is equal to 0. That means our two times, which I called x-intercepts, you might think of them as t-intercepts. They're horizontal axis intercepts. In this case, they really are t values. I'm getting that it's equal to 0 when the time is equal to 1 or when the time is equal to 4. So now, if I think about that on a number line, and since this is representing time, it wouldn't make sense to have time being any number less than 0. So instead of going -infinity to 1, you just go from the reasonable range in time from 0 to 1. Then we have the time from 1 to 4, and then the time from 4 to infinity. Now, we want these values to be greater than 0. So what I did is I plugged in a value of 1/2 into the equation to begin with, and I got -16 times 1/4 plus 80 times 1/2. minus 6, that gave me a negative. A negative is not greater than 0. So I automatically knew 0 to 1 was not a solution. Then between 1 and 4, I plugged in a 2. I had negative 16 times 4, that's negative 64. But then plus 80 times 2, that's plus 160. So I have negative 64 plus 160 minus 64. That's going to be 160 minus 120. I still get a positive 32. So you say, okay, positive 30, what does that matter? The only thing I care about, I care less that it's 32. I only care that it's a positive 32 because all positive numbers are greater than 0. So that's why I said we find that the inequality is true for the interval between 1 and 4. It gave a true statement. Now, I promise if you plug in any number greater than 4, it's going to give you a false statement. This first term starts taking over. Like if you try to plug in a 5, you'll have negative 16 times 25 plus 80 times 5 minus 64. You're going to get a negative 64 in that case. The only thing I care about it is that it is negative, and a negative number is not greater than 0, so no number in that region could be a solution. The only solution region that gave us a true statement was the region between 1 and 4. Now you have to come up with a question, should we put brackets around the 1 and 4? And a quick answer to that is no, because our problem was strictly greater than. We don't want the values in which this inequality is equal to 0. We want only the values where it's greater than 0, and that's going to be for the values in between 1 and 4. So our solution would be the interval of time between 1 and 4. So the objects will be more than 64 feet above the ground between 1 and 4 seconds. And then just to make sure it's clear, I would say excluding t equals 1 and t equals 4, because it's not true at those points. It's only true in between them. All right, guys, that finishes up this section. Please do try the homework and make sure you look at the book solutions that I do. Whether you're doing the book homework or doing the My Math Lab, the two assignments should correspond very closely.